Hello students, let's start today with the common ion effect. The common ion effect is a phenomena that is based on the Le-Chatelier's principle, and it can be defined as a shift in equilibrium on adding a substance that provides more of an ionic species already present in the dissociation equilibrium. In order to evaluate the pH of the solution resulting on addition of 0.05 molar acetate ion to 0.05 molar acetic acid solution, we shall consider the acetic acid dissociation equilibrium once again. So HAC gets dissociated into H plus AC minus. Initial concentration of HAC is 0.05 molar. H plus initial concentration is 0 molar, and acetate ion initial concentration is 0.05 molar respectively. Let X be the extent of ionization of acetic acid. Change in concentration of, if you will see, change in concentration, let it be minus X of HAC plus X of H plus and plus X of AC minus. Then equilibrium concentration, if you see, it is 0.05 minus X for HAC, X for H plus and 0.05 plus X for AC minus equilibrium concentration. Therefore, dissociation Ka, if I need to calculate, that is dissociation constant Ka equals to molar concentration of H plus into molar concentration of acetate ion upon HAC. So here H plus ion concentration is X, AC minus ion concentration is 0.05 plus X, and HAC is 0.05 minus X. As Ka is very small for a weak acid, X is much less than 0.05. Therefore, 0.05 plus X is approximately equal to 0.05 minus X, approximately equal to 0.05. Thus, 1.8 into 10 raised to minus 5, that is the Ka value, equals to X into 0.05 plus X upon 0.05 minus X. When I substitute the values, X into 0.05 upon 0.05 comes out to be X, which is equal to H plus ion concentration equals to 1.8 into 10 raised to minus 5 molar. So I can calculate the pH of the solution by putting in the formula pH is equal to minus log of H plus ion concentration, and I get the pH equals to 4.74. Next, I come to the next part of this topic, and it is hydrolysis of salts and the pH of their solutions. So the process of interaction between water and cations or anions of both of salts is called hydrolysis there. The pH of the solution gets affected by this interaction. The cations, sodium ion, potassium ion, calcium ion, barium ion, etc., of strong bases and anions, example Cl minus, Br minus, nitrate ion, ClO4 minus, etc., of strong acids simply get hydrated but do not get hydrolyzed, and therefore the solutions of salts formed from strong acids and strong bases are neutral, that is their pH is equal to 7. Let's see the other category of salts. So the other category of salts, the hydrolysis of these salts, they are of, you can see, 3 types respectively. Salts of weak acid and strong base, example CH3COONA. This results in giving you pH greater than 7 because it forms a basic solution. Salts of strong acid and weak base, this example is ammonium chloride. This results in the form giving you an acidic solution, and its pH is less than 7. And salts of weak acid and weak base, example you can see CH3COONH4. It will depend and we'll calculate the pH by putting in the formula. So let's look at the first case, that is the formation of the salt CH3COONA. It is formed from weak acid and strong base. So it is formed from weak acid, acetic acid, and strong base, sodium hydroxide. It's completely ionized in aqueous solution. So CH3COONA gives acetate ion CH3COO minus plus Na plus. Acetate ion thus formed undergoes hydrolysis in water to give acetic acid and OH minus ions there. So acetic acid being a weak acid, acetic acid being weak acid, it remains mainly unionized in solution, and this results in increase of OH minus ion concentration in solution and thus making it alkaline solution. CH3COONA gives CH3COO minus plus Na plus. CH3COO minus plus H2 gives CH3COOH plus OH minus. So the pH of such a solution is more than 7. Similarly, if you take ammonium chloride formed from weak base, ammonium hydroxide, and strong acid HCl, it dissociates completely and it results in giving you an acidic solution. So this results in the value, and the solution is made acidic whose pH is less than 7. Now, if you consider the hydrolysis of CH3COONH4 salt that is formed from weak acid and weak base. So in that case, the pH value is determined by their pK values. So pH is equal to 7 plus half pKa minus pKb. The pH of the solution can be greater than 7 if the difference is positive, and it will be less than 7 if the difference is negative. Let's look at the problem. The problem is the pKa of acetic acid and pKb of ammonium hydroxide are 4.76 and 4.75 respectively. Calculate the pH of ammonium acetate solution. So you'll put in this formula pH is equal to 7 plus half pKa minus pKb equals to 7 plus half pKa is given here as 4.76 minus pKb value is given here as 4.75. So on calculation, I get the pH of the solution greater than 7. So the answer here is 7.005. So the solution is basic in nature. Next, I come to buffer solutions. You should know the definition of this buffer solution. The solutions which resist change in pH on dilution or with the addition of small amounts of acid or alkali, they are called as buffer solution. So remember the definition, the solutions which resist change in pH on dilution or with the addition of small amounts of acid or alkali, they are called as buffer solution. Let's see the examples of buffer solution there. A mixture of acetic acid and sodium acetate acts as a buffer solution around pH 4.75 respectively, and a mixture of ammonium chloride and ammonium hydroxide acts as a buffer around pH 9.25 respectively. Let's come to the category of salts, solubility, equilibria, sparingly soluble salts. So there are three categories of salts which you can see. One is completely soluble salt, the second category is slightly soluble salts, and the third category is sparingly soluble salts respectively. So category 1, completely soluble salts, their solubility is greater than 0.1 molar. Category 2, slightly soluble salts, they come under the category 0.01 molar solution is less than its solubility, which is less than 0.1 molar solution. And category 3 is sparingly soluble salts, and here the solubility is less than 0.01 molar respectively. Let's see the solubility product constant. So the solids like barium sulfate, when it comes in contact with a saturated aqueous solution, the equilibrium between the undissolved solid and the ions in a saturated solution is represented by the equation BaSO4. Saturated solution gives barium ion plus sulfate ion, and the equilibrium constant is given by the equation K equals to Ba2 plus molar concentration into sulfate ion molar concentration upon barium sulfate molar concentration. For a pure solid, substance, the concentration remains constant, and we can write K equals to, this is for pure solid, K BaSO4, you can see K equals to molar concentration of BaSO4 upon Ba2 plus upon sulfate ion respectively there. And we call this KSP as solubility product constant. The experimental value of KSP at 298 Kelvin for the equation is 1.1 into 10 raised to minus 10. So if molar solubility is S, then 1.1 into 10 raised to minus 10 equals to S into S, that is S square, or S is equal to root over 1.1 into 10 raised to minus 10, and its value comes out to be 1.05 into 10 raised to minus 5. Thus, molar solubility of barium sulfate is equal to 1.05 into 10 raised to minus 5 moles per liter. Look at this problem, and the question is calculate the molar solubility of NiOH whole twice in 0.10 molar NaOH solution. The ionic product of NiOH whole twice is 2 into 10 raised to minus 15. Let the solubility of nickel hydroxide be equal to S. Dissolution of S moles per liter of nickel hydroxide provides S moles per liter of nickel ion and 2 S moles per liter of OH minus. But the total concentration of OH minus equals to 0.10 plus 2S moles per liter, because the solution already contains 0.10 moles per liter of OH minus ions from NaOH there. And KSP is equal to 2 into 10 raised to minus 15, which is equal to Ni2 plus into OH minus to the power 2. Ni2 plus we considered to be S moles per liter, and OH minus ion we consider as 0.10 plus 2S square. KSP is small, so 2S is much less than 0.10. Therefore, 0.10 plus 2S, approximately it's equal to 0.10. So on solving, I get the value of S, that is Ni2 plus, and molar concentration equals to 2 into 10 raised to minus 13 molar. So this is how you'll solve the problems related to solubility product constant. Thank you, children, and have a nice day.